Welcome to Chemistry Fundamentals. In this video, we'll explore four essential topics: atomic structure, chemical bonding, chemical reactions, and acids, bases, and pH. Let's get started. Module 1: Atomic Structure and the Periodic Table. We'll learn how to read the periodic table and understand why elements are grouped together. First, let's look at atomic number and Massachusetts. These two numbers tell us exactly what's inside each atom. Here's our first question. An atom of chlorine has an atomic number of 17 and a mass number of 35. How many protons, neutrons, and electrons does this atom have? Pause the video and try to work it out. Let's solve it. Step 1. The atomic number equals the number of protons. So chlorine has 17 protons. Step 2. In a neutral atom, electrons equal protons, so 17 electrons. Step 3. Neutrons equal mass number minus atomic number, which is 35 minus 17, giving us 18 neutrons. Final answer: 17 protons, 18 neutrons, 17 electrons. Key takeaway: atomic number equals protons, which equals electrons in a neutral atom. Neutrons equal mass number minus atomic number. Now let's explore valence electrons. These are the outermost electrons that determine how an element behaves chemically. Question 2. How many valence electrons does oxygen have, and why does this explain oxygen's tendency to form two covalent bonds? Think about it. Here's the solution. Oxygen is in group 16, which means it has 6 valence electrons. With 6 valence electrons, oxygen needs 2 more to complete its octet of 8 electrons. That's why oxygen forms two covalent bonds, sharing 2 pairs of electrons, as we see in water, H2O. Key takeaway: valence electrons are the outermost electrons. They dictate chemical reactivity. Elements in the same group have the same number of valence electrons and similar chemical behavior. Moving on to periodic trends. Let's learn how properties like electronegativity and atomic radius change across the periodic table. Question 3. Rank these elements in order of increasing atomic radius: sodium, chlorine, rubidium, and fluorine. Explain your reasoning using periodic trends. Let's work through this. Fluorine is in period 2, group 17, so it's the smallest. Chlorine is in period 3, same group, so it's next. Sodium is in period 3, group 1, so it's larger than chlorine because atomic radius decreases across a period. Rubidium is in period 5, group 1, with the most electron shells, making it the largest. The ranking is fluorine, then chlorine, then sodium, then rubidium. Key takeaway: atomic radius decreases across a period and increases down a group. Electronegativity and ionization energy follow the opposite pattern. Module 2: Chemical bonding. Now we'll explore how atoms stick together to form molecules through ionic, covalent, and metallic bonds. Let's start with ionic bonding. This is where metals transfer electrons to nonmetals, creating oppositely charged ions that attract each other. Question 4. Magnesium reacts with oxygen to form magnesium oxide, MgO. Describe the ionic bonding process, including the charges on the ions formed. Here's how it works. Magnesium, a group 2 metal, has 2 valence electrons and wants to lose both. Oxygen, a group 16 nonmetal, has 6 valence electrons and needs 2 more. Magnesium transfers 2 electrons to oxygen. Magnesium becomes Mg2+, and oxygen becomes O2-. The electrostatic attraction between these oppositely charged ions forms the ionic bond in MgO. Key takeaway: ionic bonds form between metals and nonmetals through electron transfer. The metal becomes a cation, the nonmetal becomes an anion, and the formula reflects charge balance. Next is covalent bonding. When 2 nonmetals bond, they share electrons instead of transferring them, creating single, double, or triple bonds. Question 5. Draw the Lewis structure for nitrogen gas, N2, and explain how the covalent bonding works in this molecule. Let's solve it. Each nitrogen atom has 5 valence electrons, for a total of 10. Each nitrogen needs 3 more electrons to complete its octet, so they share 3 electrons each. This creates a triple bond, written as N triple bond N. 3 shared pairs plus 2 lone pairs account for all 10 valence electrons, and both nitrogens achieve a complete octet. Key takeaway: covalent bonds form between nonmetals through electron sharing. Single, double, and triple bonds share 1, 2, and 3 pairs of electrons respectively. Lewis structures help visualize covalent bonding. Finally, metallic bonding. In metals, valence electrons flow freely in a shared C, which explains why metals conduct electricity and are malleable. Question 6. Why can copper wire conduct electricity, but a piece of solid sodium chloride cannot? Relate your answer to the type of bonding. In copper, metallic bonding creates delocalized electrons that are free to move throughout the metal. When voltage is applied, these mobile electrons flow as electric current. In solid NaCl, ionic bonding locks the electrons around the sodium and chloride ions. There are no free-moving charge carriers, so it cannot conduct electricity. Only melted or dissolved NaCl can conduct, when the ions become mobile. Key takeaway: metallic bonding involves delocalized electrons in a sea that flows throughout the metal. This explains conductivity, malleability, and ductility. Ionic solids cannot conduct because their charge carriers are fixed in place. Module 3: Chemical Reactions. We'll learn to balance chemical equations and identify 5 major types of chemical reactions. First, balancing chemical equations. This is crucial because it upholds the law of conservation of mass, which states that matter cannot be created or destroyed. Question 7. Balance the chemical equation: iron plus oxygen gas yields iron, 3, oxide. Try it yourself first. Let's balance it step by step. Count atoms: left side has 1 iron and 2 oxygen, right side has 2 iron and 3 oxygen. First, balance iron by putting a 2 before iron on the left. Then for oxygen, we need 3 O2 to give 6 oxygen atoms, and 2 Fe2O3 also gives 6 oxygen atoms. Adjust iron to 4. Final balanced equation: 4 Fe plus 3 O2 yields 2 Fe2O3. Key takeaway: balance equations by adjusting coefficients only, never subscripts. Start with the most complex molecule, balance unique elements first, and leave hydrogen and oxygen for last. Now let's identify the 5 types of chemical reactions: synthesis, decomposition, single replacement, double replacement, and combustion. Question 8. Classify each of these 5 reactions. Pause and try to identify each type. Here are the classifications. A. KClO3 breaking into KClNO2 is decomposition, 1 compound breaking apart. B. Aluminum plus chlorine forming AlCl3 is synthesis, 2 elements combining. C. Propane plus oxygen forming CO2 and water is combustion, a hydrocarbon reacting with oxygen. D. Iron replacing copper in copper sulfate is single replacement. E. Barium chloride and sodium sulfate swapping partners is double replacement. Key takeaway: synthesis means combining, decomposition means breaking apart, single replacement means 1 element swaps in, double replacement means partners swap, and combustion means hydrocarbon plus oxygen producing CO2 and water. Module 4: Acids, Bases, and pH. We encounter acids and bases every day, from lemon juice to soap. Let's understand the science behind them. The pH scale measures how acidic or basic a solution is, ranging from 0 to 14. It's logarithmic, meaning each unit represents a tenfold change. Question 9. A solution has a pH of 2. How much more acidic is this compared to a solution with a pH of 5? The pH scale is logarithmic, so each unit decrease means 10 times more acidic. The difference is 5 minus 2, which is 3 pH units. A difference of 3 units means 10 to the power of 3, which equals 1000. So the pH 2 solution is 1000 times more acidic than the pH 5 solution. Small changes in pH mean huge differences in acidity. Key takeaway: pH below 7 is acid, pH 7 is neutral, pH above 7 is base. The scale is logarithmic, so each unit equals a 10-fold change in hydrogen ion concentration. Now, neutralization. When acids and bases react, they produce salt and water. This has many real-world applications, from antacids to agriculture. Question 10. Write the balanced equation for the neutralization of hydrochloric acid and sodium hydroxide. Identify the salt and water produced. Hydrochloric acid, HCl, donates H+ ions. Sodium hydroxide, NaOH, donates OH ions. The H+ and OH combine to form water, H2O. The remaining ions, Na+ and Cl-, form sodium chloride, NaCl, which is common table salt. The balanced equation is HCl plus NaOH yields NaCl plus H2O. Key takeaway: neutralization, acid plus base yields salt plus water. The H+ from the acid and OH from the base combine to form H2O. This principle is used in antacids, agriculture, and industry. Let's recap what we've covered. In Module 1, you learned about atomic structure, valence electrons, and periodic trends. Module 2 explored ionic, covalent, and metallic bonding. Module 3 covered balancing equations in 5 reaction types. And Module 4 introduced the pH scale and neutralization reactions. These concepts form the foundation of all chemistry. Thank you for watching Chemistry Fundamentals. Remember, chemistry is about understanding beautiful patterns, not just memorizing facts. Keep practicing, keep asking questions, and see you in the next lesson.